At depths exceeding 10,000 meters below sea level, where pressure crushes steel like foil and darkness devours all light, titanium retains its form, yet when placed inside the very room you are sitting in, surrounded by ordinary air, this same metal becomes fragile in a different way. It fears the oxygen we breathe. This paradox is not mysticism, but a quiet chemical tragedy, one in which absolute strength exists only when matter knows how to draw boundaries. To understand why titanium is nearly immortal under pressure yet wary of the atmosphere, we must descend into molecular dynamics, where electrons quietly decide the fate of entire technological civilizations. Titanium does not resist corrosion because it is indifferent to oxygen, but because it is too strongly attracted to it. The atomic affinity between titanium and oxygen is so high that the moment the metal's surface meets air, oxygen atoms immediately bond to it, forming a layer of titanium dioxide, TiO2, only a few nanometers thick. This film is the result of self-passivation, a chemical reflex faster than corrosion itself. At the electronic level, the covalent bonds in TiO2 arrange into a stable lattice, sealing the surface like nanoscale armor and preventing oxygen from reaching the metal beneath. Remarkably, this protective layer heals itself. Mechanical scratches do not permanently compromise the surface. Oxygen instantly reconstructs the TiO2 film. This is not immunity, but risk management at the nanometer scale. Titanium allows reaction, but only within tightly controlled limits. This passive barrier explains why titanium thrives in seawater, human sweat, and even biological environments, places where other metals dissolve under ionic attack. Titanium's strength does not come from mass, but from geometry. At room temperature, titanium exists in a hexagonal, close-packed HCP crystal structure, an arrangement that balances atomic density with controlled slip systems. With a density of only about 4 centimeters cubed, titanium is nearly 45% lighter than steel while achieving comparable strength. The secret lies in its elastic modulus and the way its crystal lattice distributes. Stress force is not concentrated at a single weak plane, but spread across slip systems constrained by HCP geometry. When alloyed, by adding elements such as aluminum and vanadium, titanium can undergo phase transformations, allowing engineers to fine-tune ductility and strength. This is the art of material design, not making structures thicker, but arranging atoms more intelligently. In aerospace engineering, every kilogram of titanium that replaces steel does more than reduce weight. It triggers a cascade of benefits: lower fuel consumption, higher payload capacity, and longer service life. Strength here is systemic efficiency, and not brute force. If titanium behaves politely at room temperature, it becomes unruly at high heat. Heating titanium in air is an invitation to disaster. It reacts violently with oxygen and nitrogen, forming brittle phases that cause the metal to fracture like glass. This is why titanium cannot simply be cast like iron. The historical solution is known as the Kroll process, a carefully staged sequence of chemical reductions. First, titanium ore is converted into titanium tetrachloride, TiCl4, a colorless but highly reactive liquid. TiCl4 is then reduced using magnesium in a controlled environment, producing porous titanium sponge. This is not the final product, but an intermediate that must be further refined under vacuum to remove interstitial impurities. Thermodynamically, this process is a constant act of avoidance, avoiding oxygen, nitrogen, hydrogen, everything that seeks to steal titanium's electrons at elevated temperatures. The cost is complexity and expense, but in return, humanity obtains aerospace-grade titanium, a metal that exists only when technology becomes sophisticated enough to maintain a fragile balance between reaction and control. When introduced into the human body, titanium is not treated as an invader. The reason lies not in perfect inertness, but in surface behavior. The TiO2 layer does more than protect. It guides biological interaction. Blood plasma proteins adsorb onto the surface in stable configurations, allowing bone cells to attach. This process, osseointegration, enables bone to embrace the implant, forming a durable mechanical and biological bond. At the ionic level, titanium releases almost no inflammatory species. The immune system, exquisitely sensitive to foreign signals, finds no reason to attack. This is a subtle form of deception, not concealment, but integration. As a result, titanium has become a cornerstone of biomedical engineering, from dentistry to orthopedics, where materials must not only endure, but be accepted. Titanium is a living paradox, strong yet sensitive, durable yet reactive, cold yet biologically harmonious. Its strength does not lie in rigidity, but in its ability to establish perfect boundaries with its environment, from oxygen in the air to living tissue in the body. In the modern material world, titanium is more than a metal. It is a philosophy. True strength comes from self-regulation, self-protection, and the ability to adapt within every constraint that surrounds it.